Shalom. I'm going to be talking about the holographic complexity conjecture. It's an idea that goes back to a paper by Lenny Susskind in 2013, 2014, and by now has received contributions from a great many people, including some of the people in this room. And I want to do three things. First of all, I want to tell you what the holographic complexity conjecture is. Secondly, I want to give you some idea about why any of us might believe such an outlandish conjecture to be true. And thirdly, I want to give you some notion of the unsolved problems in this field for which we need your help. First off, what is it? The holographic complexity conjecture is a holographic conjecture, and it relates a classical property on the bulk side to a quantum mechanical property on the CFT side. Complexity, we will see, is a quantum property of a non-gravitational theory, and at first approximation, the bulk quantity that we're interested in is a classical property. And it's a conjecture. Okay, so I probably do not need to tell this audience that that is the Penrose diagram for a Schwarzschild ADS black hole. This is the sort of arena, the simplest situation in which we will exhibit the duality. That's outside the hole, that's inside the hole, and there is R equals infinity on the boundary. As you well know, if you send in a light ray from the boundary, it starts out, the sphere that corresponds to that point on the boundary is infinitely large and becomes a zero size when it hits the singularity. By contrast, if you send it across, then thanks to the Kruskal miracle, it opens up again into a second size side and goes to infinite size again. And its smallest extent is equal to the Schwarzschild radius. Now, that's what a space-like slice through Schwarzschild ADS looks like if you anchor the 2 points at t equals 0 on either side. The question is, what happens if you anchor them at some other point? If you take this slice, let's say a slice of maximal volume, anchored at times other than time 0 on either side? Well, firstly, there's a symmetry. And the symmetry says that if you boost up on the left and down on the right, or vice versa, nothing changes because it's related by that symmetry. And so if your prescription for taking a spatial slice respects that symmetry, then nothing will change. But by contrast, if you make a change on each side that does not respect that symmetry, then it does change. In particular, if you take the anchor point on either boundary and move them both up, then the wormhole lengthens. Roughly speaking, it doesn't change much outside the horizon, but inside the horizon, the length of the wormhole, the width stays approximately the same. It stays about a Schwarzschild radius large, but the length of the wormhole grows linearly with time, linearly with boundary time. Let's see that again. So there is a classical property of the bulk that tells you that if you draw a line, let us say the surface of maximal volume, for example, the size of the wormhole grows linearly with time as you drag the anchor points up. Classical property. And the ADS-CFT conjecture tells us that every classical property of the bulk is reflected in a quantum property of the boundary. The boundary state, in this very simplest case that we're considering first, is the thermofield double state. The thermofield double state is the state that corresponds to the ground state of the ADS Schwarzschild black hole. It is an entangled state between the left and the right CFT. It is defined on both the left and the right, and it is entangled between them with entanglement entropy given by the Hawking entropy. That is the state, the thermofield double state at time 0. If you evolve till some other time, then it evolves also, and its evolution is given very simply in this basis, in the energy basis, by that. And so the question is, if you believe that every property of the bulk has a corresponding property of the boundary. What is the property on the boundary that corresponds to the lengthening of this wormhole on the state defined as time moves up on both sides? The ADS-CFT conjecture guarantees that there will be such a property. It does not guarantee that that property will be simple. And indeed, the conjecture is that this property is, in some sense, the very opposite of simple. It is the most complex possible property. It is the property of complexity itself. And so this is now slightly more unfamiliar territory for this audience. What is complexity? Complexity here, I mean the computational complexity of the boundary state. Heuristically, for example, this state. Heuristically, the definition of complexity you can think of as follows. Imagine two quantum states. One quantum state is the world as it is right now, plus an electron that's spin up. The other quantum state is the world as it is right now. And now this is actually seems to be cut off by this projection system, but this is a spin down electron. It is not a spin up electron, which is why it is not the same. And the question is, what is the proximity? In what sense are these two states either near or far? Now, one notion of proximity is the inner product notion, and it is clear that this world cross spin up is as far as can possibly be in the inner product sense from the world cross spin down. Why is it as far? It's because it's orthogonal, and the inner product state admits no distance that is greater than orthogonality. These are as far apart as they can possibly be. By contrast, there is nevertheless clearly a notion in which these two are, in some sense, close to each other, much closer than they would be if the world was completely scrambled up as well. And that notion is complexity. The idea is that it is easy to get from one to the other. Here is a slightly more rigorous definition of complexity. It has the merit of being rigorous. It's also not it's not actually the best definition, and I'll come back to the end about an even more adept definition that's better adapted to the case we're considering, but let's just consider this as a working definition. It says, starting in a reference state, how many fundamental gates, it's a property of a state, how many fundamental gates are required to reach the reference state, starting with your reference state. If you want to build a circuit out of fundamental gates, how many gates are needed to reach the reference state to within some accuracy? Let me just show you that quickly. So, for example, your reference state could just be the simple product state of all down qubits, all 0 qubits, and then you can add fundamental gates. And so the gates that typically you would choose have some notion of locality, which is to say they're allowed to touch any 2 qubits, but they're only allowed to touch 2 qubits at once, say. You're not allowed to have a gate that acts on all qubits at once, otherwise you could clearly just make any state you like in one step. And then you're going to build up a circuit, a sort of quantum version of the classical circuits in your computer. You're going to build up a circuit, and in the end point of this circuit, where each of these gates just is a simple 2 unitary operation on 2 of the gates, on 2 of the qubits, you're going to build up a circuit in this manner, and the definition of quantum complexity is how many of these gates are there in the minimal circuit required to generate your state starting in the reference state. Since we only have a discrete number of possible circuits, and there are continuous infinity of states in Hilbert space, we're going to need to also give ourselves an accuracy to forgive ourselves for getting sufficiently close to the target state. Okay, that is the property that we're going to conjecture is dual to this growth to the size of the wormhole. And what's the first piece of evidence for this conjecture? The first piece of evidence for this conjecture is provided by considering the evolution of complexity of a generic quantum system. If you take a quantum system and just evolve it in a generic manner with some strongly coupled Hamiltonian, or maybe just by throwing down gates at random, for example, you can ask, what is the evolution of the complexity of a state? So we're considering an n-qubit state. Now, for an n-qubit state, the number of exactly orthogonal states is 2 to the n. That's just the definition of the dimension of Hilbert space. However, the number of almost exactly orthogonal states is exponentially larger than that. It's 2 to the 2 to the n. So if you ask not that all your states be exactly orthogonal, but that they be orthogonal to within 99% orthogonal, you will find that there are exponentially more states than there are exactly orthogonal states. This is a fact that is sometimes known as the Hilbert space is huge fact, and it is the source of most of the surprises in quantum information theory. By contrast, the number of circuits you can build out of m gates only grows exponentially with m, and that means that the maximum complexity is going to be exponentially large in the number of qubits. And indeed, you can draw the evolution of, this is number of gates on the x-axis that's been cut off. You can draw the evolution of complexity as a function of the number of gates you lay down. And what you find is that it grows linearly. The reason it grows linearly, if I just take some reference state and start randomly adding gates to it, the reason it grows linearly is that I'm highly unlikely to have made for there to be a more efficient description of the circuit that I'm making. So if I just start randomly throwing gates down, it is possible. The definition of complexity isn't the number of gates that I used to make the state. It is the definition is the number of gates in the minimum possible circuit that makes that state. So if I happen to throw down a gate and then immediately afterwards the inverse of that gate, that does not increase the complexity, even though I physically laid down 2 gates, because those 2 gates cancel out. You're highly unlikely, basically because Hilbert space is so ginormous, to have 2 gates that you lay down sequentially cancel out, and so complexity will generically grow linearly with time until it reaches its maximum value, or close to its maximum value, its exponentially large value. So you need to throw down an exponentially large number of gates before you start to get collisions and shortcuts. Thereafter, it tends to max out at its maximum value and just stay there, albeit with small fluctuations. So that's a fact about the evolution of complexity, and that gives us our first piece of evidence for the holographic complexity conjecture. In fact, our first 2 pieces of evidence. The first piece of evidence is that both are expected to grow linearly at early times, in fact, pre-exponential times. That the size of the wormhole grows linearly with time, and that the complexity of a generic quantum state acting under a generic time-independent Hamiltonian also grows linearly with time. That piece of evidence on its own should not be overwhelmingly convincing to you, since everything is linear at first order. And if it's not, if it's quadratic, you can just take the square root, and then it becomes linear. But nevertheless, it's a useful sanity check that they do indeed both grow linearly at early times. A second, more impressive piece of evidence is that they both continue to grow linearly for at least an exponential time. And that is impressive, because most properties, most coarse-grained properties one would write down about the quantum state, max out very rapidly. If you ask about the entropy, it maxes out rapidly. Most other states will max out once they thermalize after a mere polynomial time in the entropy. The complexity, by contrast, continues to grow for an exponential length of time, and therefore is a good candidate to be a dual to the linear growth of the wormhole. Okay, to get to the next piece of evidence, I'm going to have to describe more precisely how we're going to characterize the size of the wormhole. One way to do it is just to take the volume of the maximal volume slice that connects the 2 sides. A more refined way to do it is instead to use the following construction. Consider a state defined by 2 boundary times, t left and t right, and send in null geodesics forward and backwards in time from that boundary state. Then color in that state in the middle, that's optional, that step, and then calculate the action of this geometrically defined section here. As in, calculate the Einstein, Hilbert, ... whatever else is in your theory, action of that state, and divide by h bar to get a dimensionless number. And the holographic complexity conjecture is that the complexity should be roughly proportional to that action. There's actually a more refined version of the holographic complexity conjecture that I'm not going to, the so-called complexity equals action conjecture, that I'm not going to describe in too much detail, that tries to fix the prefactor. The prefactor is that complexity is equal to action divided by pi h bar. Explaining how precisely what seems to be only a multiplicatively well-defined quantity like complexity, that we can actually get an equal sign in. I will not do at length, except to say that to get this conjecture, you need to assume a conjectured bound on the rate at which any physical systems can compute that comes from quantum information theory and is sort of already existing in the literature, and then further assume that black holes saturate that bound, that black holes compute as fast as any physical system can compute. And if you do that, you get this rather handsome formula in the box. Okay, so we've seen those two pieces of evidence. The third piece of evidence comes from perturbing the black hole. So the holographic complexity conjecture is meant to be true not just of the Schwarzschild ADS black hole. If it's only true of one state, it will be a rather useless conjecture. It's meant to be true of any state, or at any rate, any holographic state that you can build in the bulk. And so what we're going to do first is take the Schwarzschild ADS black hole and perturb it by tapping it. And we're just going to tap the boundary. And what we're going to do when we see that is that in the conformal field theory, it leads to an increase in complexity, essentially due to chaotic evolution. And in the wormhole, it's going to lead to a shock wave, which is going to have in the bulk side, which is going itself to increase the complexity. And we're going to see that those two increases in complexity exactly match. Not only do they match roughly, they in fact match precisely, including a delicate cancellation. So let's see that now. So what we're going to do is we're going to take this CFT, which is evolving happily on its own under a time-independent Hamiltonian, and we're going to tap it. We're going to give it a very gentle tap, a small tap of complexity 1, namely a very small tap, a small complexity thing. And we're going to consider the following operator. This turns out to be the interesting operator to consider, a out-of-time ordered correlation function. It's called a precursor operator. And it asks the following question that I think can best be represented with this picture. It asks a counterfactual question. The question it asks is, what is the difference in complexity between the state now and the state as it would be if I had perturbed the system some time t in the past? So, for example, the precursor operator does the following. It first evolves the system back in time by undoing the time evolution with u inverse of t. Then it perturbs the system with a small tap sometime t in the past, and then it evolves the system back to the present. And the question it asks is, what is the complexity of that operation, of the relative complexity of the state now to the state as it would have been had we perturbed it sometime in the past? And the first thing to say is that there is a triangle inequality, and the triangle inequality tells you that, for sure, it cannot be more complicated, it cannot require more gates to implement that transformation than merely doing those three things in a row. First, undoing the circuit that evolved you in time to the present, then implementing the small perturbation, and then evolving forward in time back to the present. That is the maximum possible complexity that it could be. However, it could be less complexity than that. For example, if there are shortcuts, or it's for some reason easier to do than that. Here is the sort of maximal version of how complex it can be, is you take the u of t, the time evolution that you did to get to the current state, then you hit it with your perturbation w, and then you do the inverse of that time operation. That is a circuit that certainly successfully creates the precursor operator. And the question is there a simpler circuit that does it? Is there a circuit that requires fewer gates than that? Well, generically, no. If my perturbation w is just some generic chosen at random from the space of unitaries unitary, then there will generically be no shortcut, or like less than a bit worth of shortcut. But if for special w's, you can indeed get rather large cancellations that greatly reduce the complexity so that this bound is not saturated. As a very simplest case, if the perturbation is just the identity, i.e. the perturbation doesn't do anything at all, there is no perturbation, then you get complete cancellation. You get complete cancellation because the U and the U dagger just commute with the identity operator. You end up, there is no difference between the state of the world as it is now and the state of the world as it would be had I done precisely no perturbation sometime in the past. And the way to see that pictorially is to realize that once W has gone away, I can just run these gates, the U and the inverse of U, gates towards each other, and they will just cancel simply in pairs. Okay, so that's the simplest possible case. The simplest possible case is when W is the identity operator and doesn't do anything at all. Now let's choose a case that is, thank you, a case that is intermediate between not doing any perturbation whatsoever, in which case you get complete cancellation, and doing a maximally complex perturbation. That intermediate case is when you just perturb a single qubit. So when you just reach into your circuit and you just perturb a single qubit. And now you get some cancellation. In particular, this first gate over here will cancel against this gate, its inverse. They'll cancel against that inverse since neither of them touch the perturbed qubit. And so they'll just, they commute with any operator that only touches other qubits. And so pictorially, you can think of the blue qubit, the perturbed qubit, as an infected qubit, and anything that does not touch an infected qubit gets to commute straight through and cancel. But then the infection spreads, and the reason it spreads is that you then hit gates that touch both the infected qubit and another qubit, and in turn infect that qubit. And so what happens is that slowly the infection spreads throughout all the qubits, and pretty soon none of the gates can commute through because they all touch an infected qubit. And so the pattern of complexity of this operator is first that there is an exponential but still very small growth in the complexity of this operator as the infection spreads throughout all the qubits. And then finally, that it saturates, all the qubits are infected, and the complexity goes back to growing linearly with time. The time it takes for the perturbation to spread throughout all of the qubits is what's called the scrambling time, n log n, where n is the number of qubits. And so what you find is that the complexity doesn't quite saturate the triangle inequality. Instead, you get this characteristic subtraction called the switchback subtraction, given by a single scrambling time's worth of complexity. That is a signature, then, of what it looks like when you perturb the boundary state with this operator. Now the question is, what does that correspond to in the bulk? So we saw the unperturbed way to calculate the complexity in the bulk is to send in, construct this shaded region and calculate its action. Now that we've perturbed the system, it might seem as though that calculation goes through directly, because the perturbation we're putting in is very, very small, and you might think cannot affect the geometry of this system. But actually, it does affect the geometry of the system, because even though the perturbation starts out a very, very small tap at early times, the perturbation falls in, sort of 1 thermal graviton's worth. The perturbation falls in, falling down the ADS gravitational potential, and getting exponentially stronger as it does so, as it blue shifts down the gravitational potential, until once it gets close to the black hole, it's fallen so far that it significantly impacts the evolution, the shock wave significantly impacts null geodesics, and in these coordinates shifts null geodesics. And so what that means is that when you calculate, you once again construct this geometric construction and calculate its action, you get a switchback subtraction that matches perfectly. The switchback subtraction, the effect of the shock wave is first of all to chaotically grow exponentially in time, and then it maxes out at a scrambling time and just gives you that persistent subtraction. So those two cancellations exactly match. So that's a strong piece of evidence that this conjecture is either correct or is at least picking up some correct feature of holography. Right. And this not just works just for one shock wave that comes in, it works however you send in. You can imagine sending in lots and lots of shock waves. You can imagine making these shock waves not uniform on the two-sphere, but localized on the two-sphere, sending in lots of beams. No matter how you do it, the switchback subtraction you get in the boundary from the chaotic growth of the perturbation precisely and delicately matches with the change in action you get of the bulk region from the fact that the shock wave grew exponentially. The exponential growth, the chaotic exponential growth on the boundary matches the chaotic exponential growth of something falling in a ADS potential. And then you can play other games where you entomb the black hole in an inert shell and consider more sophisticated kinds of black holes and various other operations you might do. There are a great many open questions that you might wish to consider. Let me consider just the first one on this list. The first one on this list is trying to come up with a better definition of complexity, or at any rate, a definition of complexity that is better adapted to the case of interest, to the CFTs that we wish to put on the boundary in holography. There's a certain unsatisfactory element to the gate definition of complexity. You put gates down and they have to be discrete gates, so it's a discrete counting number. You need some tolerance because any discrete set of gates, for the same reason, is not going to be able to reach exactly any state that you're interested in. You're only going to be able to hit it with some approximation. And there's more arbitrariness in the definition of the basic gate set than we would desire. And so a better definition of complexity that was actually first written down in other contexts by Michael Nielsen some years ago is to try and use the tools of differential geometry to address this question. So the differential geometry are not living in the bulk. They're going to live on Hilbert space. The Hilbert space are the states of the boundary. And so in the Nielsen case, it's easiest to think about the complexity of not a state, but an operator. What you're trying to do is put a new metric on the unitary metric that reflects not the inner product distance between any two unitaries. Instead, you're going to try and put a metric that reflects the complexity distance between two unitaries. Some metric that would indeed correctly pick up that the Earth with an upspin plus is close to, rather than far from, the Earth with a downspin. And here's how you do it. You put some metric on the space of unitaries. We've cut off a bit again, but the second trace on the right is just repeat of the trace on the left. You put a metric on the space of unitaries using a complete basis of states. So the tangent space to the unitary group is the Hermitians. A complete basis would be the Pauli, choosing one of the Pauli matrices or the identity to act on the first qubit, one of the Pauli matrices or the identity to act on the second qubit, and so forth. So there's 4 to the n possible directions to go in unitary space. That forms a complete basis on UN. And what you do, so the inner product metric treats all of those directions the same. It just says it's the same distance to go in a very non-local direction as it is to go in a very local direction. By contrast, the complexity metric punishes some directions more than others, stretches the space in some directions and compresses it in others. The directions it stretches it in is directions that are highly non-local, as in directions that touch many qubits at the same time, whereas it does not punish, in fact it rewards k-local directions that are mainly the identity operator, that mainly do not affect most of the qubits and only affect a small number of the qubits at the same time. In that way, you can make a new metric on the unitary space called the complexity metric. And that's the Nielsen geometry. It gives you a nice, continuous, no need for tolerance definition of complexity, and also allows you to use the tools of differential geometry to address this question. What you find when you do that is that easy sections, local sections, sections of this geometry are negatively curved. And that's really the right answer. It's the right answer because it correctly reproduces this chaotic behavior of the precursor operators. Because the negative curvature makes the geodesics on UN diverge. And indeed means that the precursor operators do indeed get a switchback subtraction, which is now just a shortcut from following these two unitary operations by cutting the corner of those two unitary operations. It's now the geometric interpretation of the switchback subtraction. And indeed, the switchback subtraction, if you choose the curvature length right, which means choosing the punishment factors right, choosing the right metric, they do indeed precisely give you this switchback subtraction and nothing more. Nothing more because in negatively curved spaces, on the hyperbolic plane, for example, Pythagoras' theorem doesn't give you nearly so much of a switchback as it does in flat space. And then the final thing I will say is that once we have turned our baleful gaze on the physics of computational complexity, there are interesting questions that seem to have a great deal of merit and reason for further investigation, even independent of holographic complexity. For example, while entropy is certainly not equal to complexity, for example, they max out very differently, nevertheless, in much the same way that there is a second law of entropy, there seems to be a second law of complexity, a statistical law that tells you that, in the same way that the second law of thermodynamics tells you that entropy always increases, due to the great proliferation of states that also have high complexity, there seems to be a second law that tells you that complexity tends to increase. You know from thermodynamics that submaximal entropy is a resource for doing useful work. And in recent work, we have conjectured that submaximal complexity is a resource for doing useful computation. And with that rather enigmatic statement, I will leave it at that. Thank you.
Okay. Questions, please?
So your definition of the complexity assumed some specific choice of the qubits and so on. So which choice are you assuming when you match that to the local perturbations on the boundary?
Actually, with the precursor, it's not going to matter too much which perturbation you do. The generic behavior will be there even if you chose, with this more continuous definition of complexity, no matter which set you choose. But you're touching a broader point, which is that we're idealizing the CFT with a set of qubits, which is really part of the reason that we want to go to this complexity geometry construction, in which you're not describing things as some discrete set of qubits. There's some more continuous notion of the set of states.
So that was something I missed, because I thought that in your definition of the distance in the Hilbert space, because you are defining it in terms of a gate, you can only measure distance between discrete set of points. But are you claiming that this defines continuous metric distance?
That's right. So I gave two, or I guess if you include the Earths with the spins, three different definitions of complexity. The second one was about gate definition, where you literally count the number of gates that you put down. That's the sort of standard definition of complexity, but it seems poorly adapted to capture the making this conjecture precise. If instead you move to this Michael Nielsen-inspired definition of complexity, this complexity geometry, that will successfully provide a notion of relative complexity that is not a discrete number, is continuous on Hilbert space, and is just much better adapted to the situation of interest.
Thank you.
Thank you.
So what does a black hole compute? What does a black hole understand the notion of complexity boundary in the quantum mechanical theory you described, but what does a black hole compute? I mean, what is the computation?
What does the black hole compute?
Yes.
The black hole, yes, it's a rather annoying kind of computer, because it's not, the black hole just sort of does whatever it wants to do. It's not like it's playing chess or any useful computation. The black hole is not that that would necessarily be very useful. The black hole is just computing whatever time-independent Hamiltonian describes the evolution of the black hole. So, right. It the time-independent evolution that describes the evolution of the time-independent Hamiltonian that describes the evolution of the black hole can be considered to be implementable with some accuracy by a quantum circuit. And so the black hole is just doing that. It's just doing whatever that computation is.
Does the presence of the singularity behind the horizon mean anything obvious for complexity?
It is, right. So in the simplest cases that I considered here, when you calculate the action, so the answer is going to be no, but. The no part of the answer is, in the simplest cases I considered here, the contribution to the action from near the singularity is small. It's very small. One might be concerned about more sophisticated black holes or more sophisticated theories of gravity in which the contribution to the complexity would not be small near the singularity. That's a case that we're still thinking about.
Okay, I'll do a follow-up question to what Hiroshi asked, because if you remove the epsilon, do you have an upper bound for complexity using the metric definition? That's
right. So the one attractive feature, in the gate definition of complexity, there are log epsilons in the definition of complexity, which is unattractive for a large number of reasons. It is a log epsilon, so it's not making a ginormous impact, but if you read the computer science literature on these questions, there's log epsilons all over the place, and they make all of the formulas not particularly handsome. The attractive feature of the Nielsen definition, this complexity geometry definition of complexity, is that there are no epsilons whatsoever. That everything is precise. You don't need to introduce any tolerance, since you're allowed to move in any direction, albeit some directions are just highly punished, which means you can hit on precisely the target state you're after. There are no epsilons, there's no discontinuities.
Then do you have an upper bound? What is it?
The upper bound on what the complexity can possibly be?
Yes.
Yeah, it's, roughly speaking, 2 to the n. It's exponential in the number of qubits. It's if you're, the 2 most separated possible states are a state and another state where you need to evolve through pi with an operator that touches every single qubit. And that's generically exponentially large.
Okay, thank you very much. Let's thank Adam again.